everyone. Okay, the new thermal emission maps of the moon. Okay, and there's the slides. And Dylan is at Stony Brook University. And the rules are you get 10 minutes of talking, and then a warning will appear, and you have 2 more minutes left, and then 3 minutes of questions. So I think we will start right on time, actually. Okay.
Hi, I'm Dylan. I'm at Stony Brook University, where I was a former undergrad working with Tim Glotch.
There's this.
That would help.
Yes, the big one moves you forward.
This is a laser. Okay. And I've been working with LRO Diviner, as you probably hopefully heard my lightning talk, to develop these new thermal emission maps. And Diviner has 3 channels for detecting the CF feature, which is indicative of silicate mineralogy. And so the low silica mare are a different position in the CF than the high silica islands. And these already have emissivity data, but the thermal channels, which are used for detecting the surface temperature on the moon, do not have an emissivity conversion. And these channels are also broader bands. So the 2 most useful channels for to have emissivity data for will be channel 6 and 7. And that's 12.5 microns to 25 microns in channel 6, and 25 microns to 50 microns in channel 7. And there's lots of spectral features, like Rastron bands and transparency features that would be indicative of mineralogy for those channels. So when you convolve the laboratory data to the Diviner wavelengths, you can obtain a multi-point spectrum, and the narrowband CF channels are very close together once you've convolved that. And then channel 6 and 7 will be farther out, and those are integrating all of the data in wavelength ranges at that area. And that's convolved with the Diviner band passes to give us these values. So the advantage of this is that we can investigate processes we've looked at in the lab already, like darkening due to space weathering. And in the laboratory, we simulate that with adding carbon black to samples so that the fresh rock in impact craters would be the lowest emissivity. And we've confirmed in the laboratory that the darker space weather materials should have higher emissivity. This makes sense where hot objects are, or dark objects become hotter under sunlight. And the same process occurs in the mare, where the darker material is also weathered. So is there another way to? Oh, there we go. Okay. So the advantage of the emissivity conversion is that this helps us address what happens for the bulk of the Diviner data, where sunlight angles are very low, incidence angle is very high, is another way to describe that. And that is not comparable to laboratory data, where we have a fully illuminated sample in the spectrometer. So to address this issue, I've acquired a Diviner data set with incidence data and radiance data measured from the spectrometer. So at high incidence angles, the values are very low, and those are related to the low incidence angle data across incidence angle with a cosine function, which we've fitted using the MATLAB fitting toolbox. And the larger data set that I'm using to describe this relationship comes from the Diviner data within 3 degrees plus or minus latitude of the equator. And because of this data set being bimodal, I've separated that into mare and highlands areas so that the mare areas are will be higher in emissivity, and the highlands areas will be lower, and there'll be a normal distribution for each of those data sets. And so after performing the fitting, the separate mare and highlands areas come out with slightly different distributions. Because of roughness in the mare at large scales, the incidence angles create more diffuse pockets of corrected radiance. And in the mare, the flatter, rockier areas create tighter pockets where each orbit, and sometimes in each mare, which is likely the case for some of this data. So, and I've done this for channel 6 and also channel 7 someday. Oh, there's channel 7. So, and channel 7 has slightly different shape to the fits due to different photometry in each channel as a function of the band passes. And also the spectral features in channel 7 are shallower, and so that this data will come out separately in the map. To apply this to global maps, I take the global fits and perform that same transformation on the data for each pixel, which is there's a much lower volume of data, but the relationship, I'm testing whether this relationship stands for each pixel, and largely it does. And you can see that the distribution in this site at the Mare-filled crater Grimaldi near the equator on the western highlands when I've applied this transformation, creates a normal distribution with the resulting data, and brings out lots of features in on the surface that are not visible in the uncorrected data. So notably, there's a fresh crater in the bottom right of this data set in the highlands, and that is much cooler, or well, because it's much cooler, the emissivity is much lower than the darker weathered areas of the highlands. There's an issue in my correction where slopes are artificially high, and at higher latitudes, this is mostly affected in equatorial data, or equator-facing slopes of craters. And that is Highlands Channel 6. To advance all of these, Channel 6 in the Mare has slightly more orbital-to-orbit variation, and there are also fresher craters visible in the Mare. And because the lack of roughness, the peak of the corrected histogram is much sharper and narrower. Channel 7 has a much spatially less distinct variation, but you still see many of the same features, and these differences create different spectra data points that add more information to the spectra we'll be creating. So the Highlands has many similar features visible, and probably a different slope variation. The Mare has less orbit-to-orbit variation, which is helpful, and hopefully that will make the additional corrections we might make easier. To confirm that I'm masking the correct areas for each of those maps, because I'm using a mask developed by LROC, the visible camera on LRO, that uses visible albedo and morphological boundaries to identify the Mare Highlands boundary, and that's not necessarily related to the photometric behavior at mid-infrared wavelengths. I'm testing that mask by comparing the median data to the mode that's visible here. And so the mode in the Mare is right on top of the median in the properly masked data, and in the unmasked data. The masked area has a median slightly off from the mode, so that shows that I am choosing the right mask. The Highlands is not performing quite as well, and this is likely due to more slopes on craters in the, or larger craters in the Highlands and larger topography that biases the symmetry of the corrected data to higher radiance values. And channel 6 and channel 7 are largely similar in this regard. An additional verification that I've used to check that the correction methodology is working is that I've compared the radiance values at low incidence angles to the radiance values at high incidence, or for the radiance values after the correction has been applied, and plotted those against each other so that they should show up as in a one-to-one relationship. And they do, especially, and especially noticeable in the Channel 6 data is that the Highlands and Mare values are very far apart. So Highlands comes out much lower than Mare. In Channel 7, they are much closer together, which verifies the assumption we've made that Channel 7 is much more spectrally bland. And once I've combined those two masked areas together, it makes a very nice, neat map. And because of the mask, the Mare stands out more, and these values are, we'll be verifying this, but the values are probably much better quantitatively with the better fits for the separate Mare and Highlands regions. And there are areas visible along the boundary that might be more artificially seams, or they might be more artificial seams because of the mask, but we'll be comparing that to other data sets to verify if those masks are realistic. And Channel 7, being spectrally bland, has much less of a difference visible, although the seam is more subtly still apparent. After comparing this to other data sets, and then using the resulting science we can do with this spectra, we can add information to the CF position data we already have about silicate mineralogy, and use the emissivity values in channels 6 and 7 to inform the thermal physics that we've been doing with Diviner to account for that inherent emissivity of the surface. And future work will have to investigate how this correction works at higher latitudes and with different sloped areas, as well as other effects that create the orbit-to-orbit striping, like the solar distance and instrument altitude, which I haven't accounted for in this correction. There are plenty of other lunar remote sensing data sets that we can use to validate and compare this to and solve lots of other problems in lunar science. So with that, ready for questions.
All right, any questions?
I have a question. So, Dylan, what are your plans with this next? I mean, are there any specific scientific questions you're planning to look at with emissivity?
Yeah, so lots of the other work we've been doing at Stony Brook is related to albedo differences. Catherine Shirley is one of Tim's now former graduate students who has been publishing lots of information about that, including her dissertation. And so space weathering and highly silicic features, as well as swirls. I'd be very excited to check the emissivity at these channels for the swirls. In combination with the spectral libraries we build at Stony Brook using the lunar simulation chambers, will hopefully give us lots of information for thermophysical problems and mineralogical and general geology problems. So the ages of Mare regions, like in Procolarum and other areas, and the differences between Mare that now we are mostly using Wisner-IR data for, and so things like titanium abundance or iron abundance, FeO and things. Once we have spectral identifiers for those differences in mineralogy for the mid-infrared, we can be hopefully adding a lot more information to the knowledge about mineralogy and the moon. And this, with future remote sensing instruments at the moon and other airless bodies, this correction will apply in the same way. So we can expand it then too for other bodies.
So if you go back to your CF map versus emissivity.
Slowly. any other way to advance the slides? Oh, whoop, sorry. Oh.
Well, no, even if you don't go back, I was wondering if there's anything that jumps out at you when you
Well, so the distinction that I'm worried about currently with validating the correction is the Mare Highlands boundary. In the CF is probably a pretty good indicator for how the emissivity should be performing in channel 6 and 7 in the longer wavelengths. But it's overprinted a lot by impact features and fresh rock differences, thermophysical differences. So the brighter highlands areas to the east of Grimaldi show up very strong and brightly in the CF and, oh boy, and in, those craters don't necessarily appear in the same relationships based on brightness at for emissivity in channel 6 and 7, but so yeah, so that's a new feature that you don't see in the visible and you don't necessarily see in the CF. So there could be other thermophysical or geological effects going on. And there are likely small features in the Mare that relate to this, and if I look at swirls, I'll probably see some differences between different swirls. So that's a feature I'd like to look at.
Great, sounds good. We have the fun mic now.
Ooh,
Nice.
thanks.
Okay, let's thank the speaker one more time. Okay, next up is our session chair, Parvathy Prem.